Hello, YouTube. Hello, Zoom. Hello, room. We've been asked to talk about monoids. So I thought I would um, just see if we could remember a few. So uh, we need a type. We need I need a red pen. We need a neutral. And we need a combine. Okay, so what is a monoid? Well, first of all, it's an example of a structure by which we mean that we have some types and some ideas for operations that do stuff with those types. And crucially, these operations relate to each other to achieve some purpose, and they satisfy some laws which guarantee that they fit that purpose. And the point of monoid structures is to be able to combine a bunch of things into one thing. So it's about kind of aggregating lots of stuff into one result. And the example we are most familiar with, or the example we came in with, was just adding up a bunch of numbers. So one example we had was number, and we had an operation to combine them, which was plus, and the neutral element for plus was 0. So yes, and what the monoid laws tell you is that the neutral element, the zeros when you're adding up a bunch of stuff, don't contribute anything to the total, and that it doesn't matter how you group the brackets. You just pick any two neighboring numbers and replace them by their sum, and you keep going until there's only one thing left, and then that's the total. And it's just as well. We're not even in the slightest worried about which way we group them. So that's to say, the monoids give us the power to rearrange calculations so the grouping is any way we want, safe in the knowledge that we haven't screwed up getting the right answer. Is that making some sort of sense? So in particular, if you have a load of numbers that you need to add up, but you also have a friend, you can give your friend half the numbers. They can add up their half, you can add up your half, and then you finish off by adding the totals. That's the same thing as you just working your way, making a running total of the whole lot. So you're free to choose the grouping. Okay? All right so far? Cool. So let's play Hunt the Monoid. Do we know any other monoids on numbers? Don't all shout at once. Right, so the crucial thing is that the operation is to think about what's the operation that combines two things to make one, because that's what's really in the driving seat. Yeah? Multiplication. And the neutral element for multiplication is 1. So that's the thing that does nothing. Okay, right. So one reason we like to have a neutral element, by the way, is for the edge case where the collection of things we're combining happens to be empty. So the deal is, if there's nothing to combine, the answer is the neutral element. The kind of total is the neutral element. If there's one thing to combine, the total is the thing. And if there's multiple things to combine, you pick any two and you pick any two neighbors and combine them, and the result then you've made the problem simpler by having there's one fewer thing to combine. You can keep going until there's only one thing left. Okay. Do we know any more monoids on number? We've seen at least one more. Yeah. Hint, we saw this monoid in week 2 in the tutorial. Max. What's Max's neutral element? I think I heard it. It's also 0. And this is because we don't have negative numbers in our number type. There is a smallest number. So if you take max of anything in 0, the other one's going to be at least as big. All right? Whereas if we wanted to try and make min a monoid, we'd need a biggest number. And there isn't one. Okay? So that's a bunch of this stuff. Now, we also played various games involving botnum, where we said that we had B plus being a combiner with num0 as the neutral element. But also B max with bottom as the neutral element, right? Once we glue on a minus infinity, then the smallest thing is minus infinity. Okay, but it's the same stuff. Right, what happens next? Let's move to bit. Can any one of you, or better, any 4 of you, think of some monoids on the bits? Right. We're looking for a good old 2 input, 1 output operation on the bits. Guillaume's in the room and he's giving you the evil stare. And okay. And what was Ant's neutral element? Right. You got 2 choices. That's an excellent example of having a 50-50 bet and losing it. Right. Yeah. So the point is that when you feed the neutral element as one input to a monoid combiner, the output has to be the other one. Whereas when you feed 0 or false to and, you're dead. Right? If the point for and is if what do you need the first input to be to keep your hope alive that the output might be the second input? Right? You need it to be true. So that was this thing. And then I'm just going to keep. I want another 3. Or can't count. Right. So that's or. What was the neutral element for or? Yeah, that's false. So if one of your options is false, your best hope is the other one. So that's fine. But and a fine example of a monoid map that well, we'll come back to that, but that if you not the inputs to an and, you could instead or the original inputs and not the output. You know about, or some of you at least know De Morgan's laws. All they're saying is that not is a monoid map from and to or. And it's also a monoid map from or to and. And I once was told a story by a professor of computer science who was the sort of person who mixes up left and right. There's just various kinds of dyspraxia in the world. And she once took a whole undergraduate computer science exam and she got every single question in that exam perfectly wrong. She scored 0 on that exam. And the reason she scored 0 was because she muddled up in her head which of 0 and 1 was true and false. She thought 0 was true, 1 was false. She did all the calculations perfectly and correspondingly got absolutely nothing. The exam board decided that by De Morgan duality, given that the assignment of 0 to false and 1 to true is an arbitrary choice, that she had in fact got all the questions perfectly right, and they decided to award her 100 instead of 0. So it ended happily ever after. And that's monoid maps in action, right?
Let me say, please don't do that.
Okay. So do we know any other monoids on the bits? Slightly more exotic, but not much. Yes? XOR is most certainly a monoid on the bits. I'm going to write it just as XOR. And what's its neutral element? Yep. Yeah. And naturally, because once again, these things travel in De Morgan dual pairs, you should expect the thing that computes exactly not XOR should also give you a monoid. So that's the equality test, which some of us write like that. And its neutral element is, of course, true. Being equal to true is the same thing as being true. So that's kind of cool. But yeah, one thing we're really interested in, though, is not just uh, the relationship between, or the fact that individual combining operations um, uh, obey monoid laws and allow you to combine a bunch of stuff. So you can add a bunch of stuff, you can multiply a bunch of stuff, you can find the biggest number in a bunch of numbers, and so on. And you can use the same kinds of strategies for squishing them all together. But what's important is to notice that when some operations are give you a monoid, but that when you've got some operations which map the type for one monoid to the type for another, when it preserves the monoidal structure. So that was the diagram that we drew, where we said, I'm gonna do a calculation. I'll do a picture of a calculation, which looks like calculation which looks like this, and I'm going to write some red numbers, and the red numbers are going to be, I don't know, 1, 3, 4, 2, and my red operation is going to be plus. So what I'm going to do is add all these numbers up. So my neutral element, my blob, gives us a 0. 1 and 3 makes 4. 4 and 0 makes 4. 4 and 2 makes 6. 6 and 4 make 10. And what the monoid laws tell us are that it's only the numbers at the leaves that really tell us what the total is going to be. The actual internal structure of the tree is just deciding which pairs to add up in which order. We're still just adding 1, 3, 4, and 2 all together. So we're going to get the same answer no matter what the wiring in the middle is. So it's just the inputs that are important, not the wiring, is what the monoid laws tell you. So it's great when, you find out that something isn't important, because you can stop thinking about it, or you can make it the way you want it rather than the way somebody else does. Okay, but I'm going to give Clemens the exciting job of computing 2 to the power of remembering 2 to the power of all of these numbers in blue to the right of each point.
So basically, you mean I've put a 2 here?
Yeah.
And an 8?
Yeah.
2 to the power 4 is 16, I think.
Yeah.
And again, 16. 1.
Yep.
16. It's good that we don't go much further.
I'm very careful.
4.
Yes.
Well, now we go a bit further. 2 to the 6.
Yes. It was
64.
64. Do you know that there's a kind of uncanny trick? The human brain gets confused on the boundary between 5 and 6. Right, 5, 1 hand's worth, we can cope with really easily. But once things get to 6, stuff gets a bit foggy. And we can always steal a mark out of half the cohort by getting people confused about whether 2 to the 6 is 32 or 64. Just putting that little finger on that 5 versus 6 nerve is an easy way to get silly mistakes from undergraduate students. And we've known this trick forever, and we will always do it. You better watch Guillaume like a hawk for that one. So, right.
Now the most exciting one. I
Yes.
think that's 1024.
Correct. Correct. It is. Right. Now, what's going on here? I need the blue pen for one more thing.
Uh-oh.
Is that right? At each point in this picture, the red numbers tell you a true fact about addition. 1 plus 3 is 4. 4 plus 0 is 4. Now, Clemens did the operation 2 to the power on all the data. And the good news is that because 2 to the power is a monoid map, not just any old function, it's a monoid map from addition to multiplication. So each node also tells you a true fact about multiplication. 2 times 8 is 16. 16 times 1 is 16. 16 times 64 is 1024. So it's not just that we transform the numbers, it's that we transform the entire diagrams that tell truths about combining those numbers. And that's an extremely useful thing. You know, saying that we have a monoid map is saying that we have some sort of distributive law. So here we are saying that 2 to the power of A plus B is equal to 2 to the power A times 2 to the power B. And of course, we also had that 2 to the, got it, better not make a color mistake, 2 to the 0, yes, equals 1. Now, these are, of course, laws you learned about exponentiation at school. You weren't necessarily told that they traveled in pairs like this, that there's a law for plus and a law for 0, or why one should expect a law for 0 when one has a law for plus. You know, and that somehow it's no accident that we're talking about 0 and plus which make one monoid, 1 and times, which make a different monoid. And you were also not taught why this has anything to do with the thing they called the distributive law when you were at school, that talks about how multiplication sends addition to addition. My point is that it's all the same stuff behind the scenes, that monoid maps give you distributive laws, and distributive laws enable you to massage the structure of the formulae that you work with when you're trying to solve equations. We did that over and over again. You know, we used the distributive law of multiplication over addition in the course of showing that multiplication is itself associative. Okay? So let's see how else we're doing. It's 25 to. I'll tell my story about sorting another time. I want to show you a thing, an important thing. Consider some function, which I should stop writing quite so multicolored, but you know, I like doing that.
Two on paper.
Yes. Right. Suppose we know some type. Suppose we've got a monoid. Let's say we've got a monoid T with a combiner and a neutral element nu. We've got some function from number to T. Now, if somebody just tells you that you've got a function from number to T, just a function, could do anything, then, you know, you get to choose freely a T, an element of T as the output for any given input number. So you got to choose f of 0, you got to choose f of 1, you got to choose f of 2, and if you're just told f is a function, then there's no necessary connection between any of these numbers. It's just random buckshot, you know, could do anything. No clues. If, on the other hand, you are told that f has to be a monoid map, then you're very, very lucky indeed. Because, well, if you're told that f is a monoid map from addition to T, yes, so f, yes, f, a monoid map from plus to T, then what does that tell us? What if I say what's f of 0? It's a piece of paper, so I'm allowed to use Arabic numbers, right? So, right. So here's one of these things where the superpower that you have at the moment is that I haven't told you what T is. I've just told you that we've got these operations which make it a monoid. So you need to use the fact of total ignorance in your favor. Right? Okay, so you know that F is supposed to be a monoid map from plus to, oh, sorry, from plus to, I should say, to this combine operation. What are we going to send 0 to? Do we have a choice? If we want a monoid map. Right? If we want a monoid map, we have to send the neutral element of plus to the neutral element of the monoid we're going to. Otherwise, we break the rules. Okay. So we've got the base case of a definition. Okay. And what's the next thing we usually do? I mean, if we're working inductively over the input, is we need to figure out, yeah, what f of one plus n is.
Usually written as 1 plus.
Right. Successor of n is otherwise known as 1 plus n. That's an example of using the freedom to compute any way we want. So yeah, we don't know what this is. We need to figure out what this is. But we know F is a monoid map. So what do we know? Yes.
Well, we know something.
Yeah.
We
Um,
know that it distributes, so
Yes. Yeah. So we
should somehow f of 1 plus f of n. Otherwise, we're in trouble.
yes, F of 1.
And not plus of
Yes. Combine, whatever the combine is.
mistake, you have to put the new operator with it.
Yes.
Yes.
Yeah. So if F is a monoid map, then there's no choice. This has to be true. And it looks most of the way to a definition. You know, that's a nice, you know, recursive call on something smaller. So the only freedom we have in this picture, potentially, is to choose the value of F of 1. And yeah, so this tells you something important, is that if you know you've got a monoid map out of plus, you know that the only interesting information is where 1 goes. That tells you something nice as well. You know, for example, let's suppose that T is also number, and that this combination is also plus. Then F of 1 is some number. What's F doing? Let's suppose this thing is also plus. And F of 1 is M. What does F compute? Sorry? Doesn't quite compute M. So if we're taking this to be the definition, then we're counting how many addings up of M to do. So obviously we're sending 0 to 0. If our target monoid is also numbers with addition and 0, then we've got this turns into, let me make it more concrete, that F 0, 1 plus what does this program do? I realize it's outrageous that I'm asking you to read a program and tell me what it does just by looking at a piece of paper, not by typing it into a computer and trying it out. What is going on? I'm sorry to break it to you, but looking at a program written on a piece of paper and figuring out what it does is a terribly important skill you're all going to have to learn. Because if you're sitting there looking at your own program on a screen, thinking, I don't know what the fuck that does, then you're not a very useful computer programmer. Yes. What's this doing?
You might have seen it somewhere.
You've seen it? Yes. No, there's no taking away going on. Yes. Yeah. So for every one in the input, for every 1 plus in the input, there's an m plus in the output. So what's going on?
Take f of 2, it's m plus m.
Right. So if your number on the input side is 1 plus 1 plus 1 plus 1 plus 0, right? It might look like that. Then your output is fine.
Have you read the Magic Bird?
Actually, yeah, I should have written that in black, of course. Right. Right. Our original n was made by adding up n ones. That's our input. Our output is made by adding up n m's. So what have we computed? Multiplication! So this is the thing we've been calling m times n. All right. So this tells us not only do we know, because we know that multiplication has a distributive law, it behaves like a monoid map. We know that the only monoid maps from adding to adding are the ones that multiply by something. There aren't any others. What's more, the fact that just choosing where you send one determines the whole operation is why multiplication is a sensible thing to invent in the first place, and why it can't help having a distributive law. It couldn't fail to have a distributive law, even if we wanted it to, because we invented it in such a way that forces it to have a distributive law. So that's where this is coming from. So, okay, message is that monoid maps out of adding are determined by where they send one. Back to this picture, we got a monoid map from plus to times by deciding to send 1 to 2. That was the choice we had, that we were doing 2 to the power. And you'll find that every monoid map from plus to times is some sort of exponentiation. You decide what to send 1 to, and it's then, if you're sending 1 to x, then your monoid map is x to the power. And that's the shut up alarm. All right. Yeah. But the point here is that what we just did to invent x to the power and what we just did to invent multiplication was the same thing. We were constructing a monoid map out of addition by choosing where to send 1. The only thing that happened differently was that we switched out the target monoid being plus to the target monoid being times. And the same thing works over here. So for example, if our target monoid is XOR, then we have a monoid map that sends 0 to false for sure. If we send 1 to false, we'll get a boring monoid map that always sends everything to false. So the interesting thing to do is to send 1 to true. So we get the operation that sends 0 to false and 1 to true, and XORs all the things. So that's the test on numbers that says whether a number is odd. And you know that if you add 2 odd numbers, you get an even number. And if you add 2 even numbers, you get an even number. But if you add an even number and an odd number, you get an odd number. This is also something you were taught at school. And nobody told you that it's just the distributive law again. It's the same thing as the distributive law for multiplication over addition, except we've just picked a different monoid. We've different carrier, we've picked the bits, we've picked XOR, we decide where to send 1, job done. You know, the fact that you got some laws just came from the business of building the monoid map. So the message is that there's so much structure that shows up over and over again. And when you've got the awareness to notice that the idea in front of your face is not a new idea, it's the old idea again, just with different data, and you realize the skills you learned at school are useful in so many other places. You know, we end up with these monoid maps give us a notion of multiplying out, and you learned multiplying out with plus and times, and, you know, rearranging calculations using multiplying out. Well, you can rearrange all sorts of calculations using multiplying out, and the fantastic news is that you already know how to do it. It's just that you don't necessarily notice that that's what you're doing. And I want to teach you to notice that that's what you're doing, because there's going to be a lot of it about. Okay, I think we've reached the end of our sensible time. I'm going to say stop recording.